So now we are going to talk about some micro and nanoscale carbon structures and devices. So we have already discussed large-scale carbon materials. We have talked about making electrodes using graphite and glass-like carbons. We have also talked about catalytic beds using activated carbons and so on. Now let's talk about some micro nanoscale devices. So if you remember from our micro nano fabrication class that we discussed the scale at which we are talking about, right? So 1 micrometer equals 10 power minus 6 meter, and 1 nanometer equals 10 power minus 9 meter. Okay, so now for a device to be called a micro device, the functional element should be smaller than micrometer, 100 micrometer. And in the case of nanoscale device, the functional element should be smaller than 100 nanometer. So you can imagine that there are difficulties in making these devices, right? Because now more than the material properties, the manufacturing becomes complicated. Why? Well, because for large scale manufacturing, first of all, we already have a lot of techniques available. And also, whenever there is something that you can touch, with your hands, slightly larger than that, even that is possible. When you can operate things with your hands and when you can see the material or see the structure with your eyes, naked eyes, in that case, it is much more convenient for us to make something. But if something is in the, our material itself or the structure itself is in the nanoscale, there is no possibility of looking at that material without using a very high-end microscope. You can definitely not pick that material using a tweezer, or you cannot hold it with your hands. So in that case, actually, even though the fundamental principles might be simple of photolithography or various other similar techniques, the fact that these materials are so small, it is not very intuitive, how you handle them, how you hold them, how you deal with them. So in that case, the manufacturing processes become little bit different. Okay, so let's talk about, so when we talk about micro nanoscale devices, what carbon materials come to your mind first? Okay, so first you think of carbon nanomaterials because they are of nanoscale, so we can of course make nanoscale devices using them, which is correct. Okay, you can also use them at larger scale, but you can also definitely make nano and micro scale devices for sure using carbon nanomaterials like graphene and carbon nanotubes and fullerenes. And there are also some other materials that I have not discussed in this course, for example, graphite whiskers. So there are materials that you can use, and then also you have fullerenes that are embedded inside a carbon nanotube. These are called p-pod structures. So there are still many structures that we did not discuss, but okay, we have discussed some primary structures. Okay, so nanoscale materials definitely. What else can be used at micro scale if not nano? Glass-like carbon. So glass-like carbon, this is what we learned in our photolithography section, that you can actually, certain phenol formaldehyde resins can be photo patterned, and well, using the same principles as we did for the bulk, we could convert them into carbon and get our carbon devices, carbon structures. Okay, now structure and device also, you understand the difference. Structures are not functional, but devices are functional. Okay, so well, glass-like carbon can be used for this purpose. Similarly, activated carbon also. See, in the case of carbon, we are using some polymer, patterning it, and converting it into carbon. That is what we did also for large-scale structures. For graphite, we used not polymers, but let's say needle coke or other precursors to carbon. So the idea is that use some precursor, give it a shape. That's what we do also in the case of carbon fibers. So why not in the case of micro nanoscale? So in fact, this is it's very easy to translate our carbon materials or to make micro nanoscale devices using carbon materials, because of the fact that a lot of lithographic techniques or micro nano fabrication techniques are compatible with polymers, and polymers are our precursors. Organic materials they have been our precursors. So in fact, that is the reason it is indeed easy to convert. So even if there is I was saying about activated carbons. So if there is a precursor which yields activated carbon instead of glass-like carbon, so it goes through the charring process rather than the coking process. In that case, that can also be used, and we can use porous carbons also in the case of small-scale structures. So this is what we are going to discuss. Again, I would say, like in the previous lecture, that I'm not going to give you too many examples because it's also not possible for me to cover all the examples. at one place, but we are going to at least compare different techniques and different carbon materials that can be used at micro nano scale. Okay. So here I have mentioned some more names: graphene, carbon nanotubes, vapor grown carbon fibers, again fullerenes and so on. Okay, now let's come to the device fabrication aspects. So the title of this slide says that these are going to be top-down approaches that we are going to discuss in this lecture. Top-down approach is your photolithography followed by carbonization, or any lithography followed by carbonization. Another top-down technique, if you can think of, well, if you can use carbon fibers in your micro nanoscale devices. I also told you that carbon fibers, well, in the case of composite materials, they are used at large scale. They are used definitely, as CFRCs, they are used for making very large structures. But at the same time, you can directly use these carbon fibers for making micro nanoscale devices, especially different kinds of sensors and membranes and so on, even electrodes, because they are high surface area structures. So in that case, another technique that you can think of is electrospinning. So you can make something using electrospinning. It is a top-down technique, right? You're making fibers, you're pulling fibers. So it's and then we are removing the non-carbon atoms from it. So it's subtractive. So carbonization is actually always subtractive. So these are the top-down approaches for making carbon-based structures devices. So here are some nice pictures that I have shown. This particular AFM tip that is made of carbon, first we made it using some polymer, acrylic polymer, and this was used, fabricated using nanoscale 3D printing. Okay. Now you also have phenol formaldehyde resins. So what are the precursors? The same precursors that you have for large scale glass-like carbons can be used at micro nanoscale. The only difference is that your heat treatment temperatures are relatively lower. So you may not have the exact same properties as you have for large scale glass-like carbons, but you will have properties reasonably close to it. Okay, so well, you can use not just phenol formaldehyde resins, also furan resins, acrylic polymers, and maybe some other polymer will give you a good carbon. There are certain hydrogels also which give you good quality carbon, and whether or not it is glass-like carbon, that is something you have to see. You have to perform certain experiments, see whether you know what is happening to your structures, whether they are getting deformed because of the coking process or not. So these kind of experiments you can do and then figure out. But definitely many high carbon containing organic polymers can serve as a precursor. Okay, so you can get these kind of structures. So this is some pattern, again lithographically patterned structure, which then you convert into carbon via heat treatment. Heat treatment temperatures are relatively low. Plus there is one more little challenge here. The fact that your structures, whenever you're performing lithography, you have a certain, let's say, silicon wafer, you have a substrate. On top of that, you're doing your spin coating in whatever the fabrication that you're performing. It is substrate bound, which means you need to place the substrate also inside your furnace when you are performing the heat treatment, and that is why the heat treatment temperatures are also limited by the surface. And another problem, limited by the substrate. Another problem is that you also have non-isometric shrinkage. What does that mean? Typically, if you have something in in space or a freestanding structure, it will shrink from all sides. But in the case of surface-bound structures, then you have one side does not shrink as good as the other sides. We had discussed this in the past anyway. So this is basically the idea. These are the challenges that you have to think of. One interesting thing is that now we can use carbonization as a tool for converting microscale structures into nanoscale. So if our fabrication technique can only give us microscale structures, but still now because we can utilize the dimensional shrinkage and we can actually convert microscale structures into nanoscale. Why would we do that? To further increase its sensitivity or further increase the surface area. Okay. Often you would also use a combination of different techniques. So for example, you can use electrospinning with lithography. So here is an image that I have shown here. So you have two contact pads. On top of that, you see there is a fiber. So now the fiber was made using electrospinning and in such a way that you got only one single fiber. We don't need to go into the details of that. And the other structures, the electrode structures, they are made using photolithography. So, and then you carbonize everything all together. So when you carbonize everything together, then you also have, it's like a monolithic structure. Monolithic means everything is made of same material. There are no joints. There are no junctions. There are no additional contact pads and so on. Carbon is electrically conductive. So you can also utilize all of these properties, and you can also use a combination of different fabrication techniques. So there are also several cell culture scaffolds is one example, where because carbon also happens to be biocompatible, especially this polymer derived carbon, the glass-like carbon, something that is similar to glass-like carbon. So this also these kind of materials can then be used for making cell culture scaffolds and substrates and so on. So there are variety of materials, or variety of applications that are possible with micro nanoscale carbon structures, right? You can also use the combination with other materials, for example, ceramics and metals and silicon and whatever. You can also, because at micro nanoscale, often you're using multiple materials. So if you want to make a large scale graphite electrode, that's probably just a cylinder of graphite. It will have some connections with the rest of the, but you will typically fabricate just the graphite cylinder. But in the case of micro nano devices, when you're making something, typically you would like to make a complete device, which means that you have to work with not just carbon but also various different materials, which also leads to sometimes certain problems that we are going to discuss soon. Okay, so now we are going to talk about the bottom-up approaches. Okay, when we talk about bottom-up, means we want to build something up. So what is a technique you can think of? Not lithography, right? Lithography is top-down. Printing. So if somebody asks you what is the most common technique for making carbon nanomaterial based devices, well, that is printing. So what you are actually doing is you are making an ink. Printing requires an ink. So now this may not be your simple inkjet printing, but it may be some specialized type of printing where the structure sizes are very, very small. Maybe micro scale, maybe even nano scale. So these kind of printing techniques can use inks that are made of a certain pigment, and that pigment is your graphene. You know that, you remember from the carbon black lecture, that even 3000 years ago, people were using, especially in India, inks made of carbon. Carbon was used as the pigment. So this can also be, this is something that is already well known. All you need to, however, do is to make sure that you have the right interface properties between your carbon nanomaterial and whatever is the binder or the medium that you have used. So commonly used technique one is this is, yeah, you will see this these two black patches in this image. So this is an example of devices, graphene based device. So you can use graphene or carbon nanotubes or any other carbon material. You can make an ink, and then you can make large scale patterns also. Very small scale to large scale patterns can be made using these materials. Okay. However, you know this, and also in all the nanomaterial lectures I have mentioned this multiple times, that when you're using a bulk nanomaterial in bulk, then you're often compromising the properties. So you're not going to get the properties of single graphene sheet or single carbon nanotube when you're doing printing like this, and when you're really making a bulk type of structure. So your properties will be definitely compromised. Still you can get reasonable properties. Okay. So there have been examples also of a single or a few carbon structures. So this example, for example, you see if in this image, what you have here is two contact pads, and between them you have carbon nanotubes. So you can actually also sometimes grow carbon nanotubes onto your contact, especially if it is a metal contact, because you know that transition metals do serve as, at least some of them serve as a catalyst for carbon nanotube fabrication. So you can even mix these catalytic particles into your polymers or any other substrate for that matter, and then directly grow on top of it your carbon nanotube. Or you can use metal contact pads, and then carbon nanotubes can be grown in an aligned fashion as well. So this is an example where you can use few carbon nanotubes. Also single nanotube and graphene based devices have been fabricated, but none of them have been fabricated at a large scale, at least as on date. Okay. So other than printing, whatever techniques that you can use for bulk material, also spraying and different kind of coatings can be made using these using carbon nanomaterials. Okay. They can also be mixed in other carbon materials and then further carbonized, similar to how we make composites and so on. Okay. The application areas are way too many. So you can make transistors, you can make electrodes of various kinds. So when I say electrodes, they can be electrodes for sensors, and again sensors, there are a lot of sensors, biosensors, chemical sensors, optical sensors, surface sensors, a lot of things. Okay, so you can make a lot of things with carbon structures. Basically what you have is a nicely conductive and mechanically strong nanoscale material, which can be synthesized in principle. In many cases you can even purchase them. Okay, so yeah, one application of carbon nanomaterials is also as an additive in the composite materials, and there are many techniques. So here again I have shown an example of 3D printing, nanoscale 3D printing. In this case also you can use similar inks that you used for 2D printing, right? If 2D printing is possible, 3D is also possible. All you need to do is slightly change the viscosity properties of the ink. In some cases, for example, in the case of 2-photon lithography, this is also kind of 3D printing at nanoscale, but you're cross-linking your polymer using a laser. So these kind of techniques can also be. A lot of techniques that are available at nanoscale are in a way suitable for making polymer structures, and polymer structures can be converted into carbon. That is number one. And number two, you can also use, mix your nanomaterials into polymers and then further use these techniques. Then you can also carbonize. So you can use, now basically you're using a good combination of bottom up, top down, all kinds of techniques, because often this happens in the nanoscale devices anyway, that you use a combination of various techniques. Okay, so now let us talk about some primary challenges when it comes to carbon-based micro nanoscale devices. Not just for carbon, but for all small-scale devices, often it happens that since you're using multiple components in a very small area, the footprint is very small. So you're using some metal contact pads, you're also using a silicon substrate, and then you're using certain types of maybe glue, binder, because you need to attach one material on top of another, and everything needs to be done at micro nanoscale under microscopes, and many things are automated, but some things are done by hand. So working with multiple materials in itself is a challenge at micro nanoscale, and definitely that is also important for carbon materials little bit more, because carbon materials have, number one, they are very light. So dealing with carbon nanomaterials is extremely difficult, and that is why I would again like to mention, think about the health safety when you're working with carbon nanomaterials, because we don't know too much about the long-term effects of the presence of carbon nanomaterials inside your body. Those studies are still ongoing. So think about it. But anyway, the point is that if you're wearing proper masks and everything, then it's all right to work with these materials. But they are so light that often it's very difficult to handle them. Okay, and also they get electrostatic charge, so it's very difficult to place them somewhere and to handle them. So handling is also a little bit of an issue with carbon nanomaterials. Okay, other than that, what are the important factors? So I have listed a few here. First of all, you need to select the right fabrication technique, which could be a combination of two fabrication techniques. Okay, so that you understand. Okay, selection of precursor, especially in the case of the top-down type processes, because not all precursors, even though we have many polymers, but the selection rules are still the same that we had for large-scale materials. So you may not get good quality carbon, because the organic content, either the carbon content is too low in the polymer, or you have too much oxygen in the polymer, so it gets, it takes a lot of carbon away, so you don't get good quality carbon. So the coking charring mechanism in all the fundamentals of what gives you good carbon is also valid in the case of micro nano devices. So selection of precursors is very important. Optimization of dimensional shrinkage. So this is also in the large scale structures, that is a problem. But here the only additional factor is that you have a substrate. So in one dimension you do not have the same shrinkage as in the other directions. But you can optimize it. You can do shape optimization even using a lot of CAD software. You can do this, and then you can further, accordingly make your polymer structure. Okay, in the case of printing, one very important thing is the interface. So it is like all the composite materials. Whenever you're mixing one carbon material with some polymer, or any other material, even water for that matter, but typically you will use organic inks, organic binders in the inks. In that case, the interface properties are very, very important. Otherwise, your structures will peel off. Or also, you will definitely not get the same properties as you expect. Okay. One very, very important thing is what is known as the contact resistance or the interconnects between. So whenever there is a one carbon material, let's say, and then you have a metal contact pad. Why would you have metal contact pads? Because you need to complete your circuit, right? How do you, because ultimately you need to get some readout from your device. It is measuring some property and giving you some signal, but you need to have a circuit in order to receive that signal and to somehow convert it into the right format of the readout. But to make these circuits, now you will need some contact pads, some like, what is you will have in the large scale, you will have wires and cables. In the small scale, you may often have these flat electrodes, or even the wires are then printed like on top of your credit card. These are like printed metal, thin films of metals. So you will often have them in combination with the carbon materials. And there, what you have is something known as the work function difference between carbon and the metal. Work function basically means the energy or the thermodynamic work that is required to pull one electron out of a material. So pulling one electron out of carbon and pulling one electron out of metal require different types of energies, and that is why when there is a flow where there is a transport of electrons, sometimes your contact itself, the contact where this is the interface again between metal and the carbon material, there it may offer a lot of electrical resistance. Or not a lot, but significant. Something that does interfere with your signal. Maybe if you have a sensor which already gives you very, very, very small, reading, and then you have contact resistance. In that case, it can often become a challenge. And so this is one issue that needs to be solved. What you typically do is, let's say here I have a metal or any substrate, and then I have a carbon nanotube. Somehow I was able to place it on top of that. Single carbon nanotubes, it's nanoscale, right? But somehow, let's say, under the microscope, using certain specialized techniques, I was able to place this carbon nanotube across this contact pad. But now I need some other sort of glue. Glue, or that glue could be another metal. It can be platinum. You can use ion beam, deposition of this platinum. But something else, you need to hold your nanotube there. This is where I'm talking about the contact resistance. Because now you have multiple these structures, and at that scale you don't know if the adhesion is good or not. So in that case, this is what we are talking about. What we can also do is take a silicon oxide substrate. So silicon oxide looks like this, so at least it gives the impression of this purple pink color because of the refraction of light. But that is why a lot of graphene pictures that you will see, they look purple, but the graphene is not purple. It's the substrate, which is your silicon oxide substrate. You will, let's say you have a graphene flake on top of silicon oxide, and now what you can do is, from on top of that, you can then sputter your metal contact pads. But in this case, you will see I have made much larger contact pads compared to what we had in the case of carbon nanotubes. So you may have to play with these fabrication parameters a little in order to get your optimum performance from your device and reproducible. Okay. So altogether, we have other limitations such as the heat treatment temperature that you already know that we cannot go above, in principle, 1400, because 1400, if you're using silicon substrate, because 1400 is the melting point of silicon. But even you will not go to 1400 because sometimes at lower temperatures also you can have thermal fatigue if you're performing your process very, very slowly, heat treatment process. So generally you will not go above 900, 1000 in the case of micro nanoscale devices, and this is what I'm talking about, silicon substrates. Of course, if you use a substrate that can go to very high temperatures, maybe you can use slightly higher temperatures. Okay, so this is one limitation for sure. One more interesting thing is that the characterization. So characterization techniques, whatever we have talked about, XRD, Raman spectrum, they require a reasonable amount of your material, at least a few micrograms, in some cases even milligrams. So that is very difficult. The electron microscopy is easy for nanoscale material, okay, especially transmission electron microscopy, that is okay. In fact, it's more convenient compared to bulk materials because your sample is already very, very small nanoscale. So, you know, the challenge of making TEM sample is relatively less. But on the other hand, for XRD, which is, you know, that is a very, very important technique for us, the sample sizes are often very small. And the problem is also that, so here I have shown one pillar, carbon pillar, which is 2 micrometer in height and 1 micrometer in diameter. When you have a structure of that dimension, that means it has a very high surface to area. That means it will carbonize fast. And maybe at lower temperatures, it has more crystallinity than your bulk material will have, because the pores can release easily, because the defects can anneal out easily. Now, what does that mean? That means that my properties of this pillar are not the same as the properties of bulk material, which is prepared at the same temperature under the same conditions. So I need to do specific characterization for that pillar. Now, if it is that small, it's really difficult to perform XRD for it, and also it is substrate bound. So these are some of the challenges that you need to deal with. Okay, maybe you can make an array of such pillars, or maybe you can make a lot of them, somehow etch them out of your silicon, but it's often a lot of effort to have enough sample for using characterization techniques that can be used for large scale materials. Or of course, you can also perform some modifications, perform single crystal XRD and so on, but all of them have their pros and cons. Okay, yeah, so this is what I have written. The properties of bulk do differ from what you have in micro nanoscale, especially when it comes to you know, something that is prepared by heat treatment. Okay, so finally, let's talk about some flexible carbon devices. So this is actually not as complicated as you think. What is flexible? Flexible is anything, you know, this is flexible, right? This is flexible. So anything that is flexible and also wearable. Sometimes you have these, nowadays I see everybody wearing a watch which tells them how much do they walk. Those kind of devices, those watches that tell you what you're doing, they require a battery, right? And their battery should also be flexible, potentially, you know, in principle. Whatever electronics they have, some, you know, printed circuits, they should also be flexible. Only then you will have a perfectly flexible watch. So those kind of devices. Also nowadays you hear of, you know, flexible electronics. You will have your computer screen which can be bent at a certain angle. Your mobile phone can have a you know, some flexible structure. Those kind of structures, devices, are known as flexible devices structures, sometimes also called bendable. Okay. Sometimes they're also called organic electronics. Don't get confused. Organic, basically any polymer is organic, and often the material that you're using in these flexible, so the flexible substrate, instead of silicon, for example, if I use a flexible substrate, that substrate is most likely going to be a polymer. And since polymers are organic, so that is why they are called organic. This is called organic electronics. But yeah, organic does not mean biodegradable. Organic does not mean anything. You know, just think of it as flexible devices. You can also potentially make them using inorganic materials. In fact, when they're making, when we read about flexible solar cells, photovoltaics, a lot of often there are thin films that are made of inorganic materials. So it doesn't have to be organic electronics. So it's better to call it flexible electronics. Okay. Yeah, so how do you make now something flexible with carbon which is hard and brittle? Most of the forms of carbon are hard and brittle. Unless you're taking a single carbon nanotube or single graphene sheet, yes, that is wavy and that is flexible. But that is single graphene sheet you're hardly using in devices. So whenever you're using, again, even if you're performing printing, then you're using the entire thing in bulk. So, and if you're using any large scale carbon material, that is going to be hard and brittle. Even carbon fibers, if you think of the properties of the carbon, the carbon itself is hard and brittle. It is the structure that we give to it. When we pull threads out of it, when we make tubes out of it. So it is the large scale structure that we, that we give, that we make. That is what can be flexible. Carbon itself by nature is not flexible, but we do have a lot of flexible devices using carbon. You will see, first of all, you're doing this printing, right, with nanoscale materials. Printing with an ink can be done also on a flexible substrate, right? So that is one technique actually of making a lot of flexible carbon devices. Okay, so that is technique number one. So let me also tell you all the techniques. The first one is printing carbon nanomaterials using onto a flexible substrate. This is an example. I have found this picture somewhere. So here you have graphene oxide. So it's also a related material. You can have carbon nanotubes. You can have graphene itself, multi-layer graphene. So you can make a ink, and then you can print these devices. And typically this orange color substrate that you see, these are polyimide sheets. But you can also use any other sheets, any other flexible polymer, even PDMS, any flexible polymer if you want to make flexible devices. Okay, so that is the technique number one. What else can you do? So we always carbonize polymers, and you see this polyimide substrate here. So don't you feel like carbonizing it? Yes, this is what we can do. We can use something like a laser to locally induce heat and carbonize the polymer substrate itself. So then you're kind of writing using a laser. So here is an example. Okay. However, the property of carbon, the quality of carbon is not going to be as good as, well, any of the large scale carbon materials, even if you induce very high temperatures. The reason is that the process is happening extremely fast. So it is not happening in the case of when you keep something inside the furnace, then you anneal it out at very low, very slow ramp rates. So 5 degrees centigrade per minute, or even slower, even lower than that. So there you have, you're providing your material enough time. All the gases, byproducts, stars, whatever is coming out of it, you give it enough time to release. Also, you have some nitrogen in your furnace which pushes these byproducts out. That is not happening in the case of laser carbon. Number one, the process is very, very rapid, so it leads to a lot of porosity. Number two, these materials, these kind of carbons, have a lot of impurities because some of the tars and byproducts, they redeposit. Okay, but you can get reasonable properties, and this is also reasonable electrical conductivity. So this is another method of making flexible devices using carbon. What else? Yeah, so you can make carbon fiber mats, that from electrospinning and also from melt spinning. So carbon fiber mats, carbon fabric, What you can do is you can pattern it. Now, patterning it in micro nano scale is not easy. It can get very complex. You may have to mask your structures with certain metal masks even, and then perform reactive ion etching and so on. But it is possible. So here is one example where you take this carbon cloth like structure and pattern it in the micro scale, and then make this very highly flexible device out of it. So this is a neural sensor made using this kind of carbon fabric. So this is another technique. What else? You can also use ultra thin carbon sheets. So even you can get glossy carbon sheets which are very, very, very thin, and they are relatively flexible. But there you of course have limited flexibility. So flexibility, whenever you're making certain device, then you often need to test how many times it can bend before breaking, and not just bend, but it should retain its properties. And often you will do these kind of bending tests like thousands of times. Only then you will say, this is a stable, flexible structure. And of course, the interface properties of these, even when you're performing printing. So even when you're performing printing, your film, this film-like structure should not peel off. So this peeling off from the substrate is also one of the challenges. So here, when I'm talking about interface, it's about the interface between the substrate and the pattern structure. So this is an important thing. And as I said, thousands of bending cycles you need to evaluate before you can think of using this material for a regular application. Okay.